Yes, so part one, we looked at scalars and looked at fields, we looked at vectors. Part two, we looked at um, directional derivatives. Now we're part three, we're going to be looking at surface normals. Since the gradient of phi is perpendicular to the equal potentials, surfaces of the function phi, if we have a surface different than phi defined by phi at xyz is equal to a constant. So our function phi has to be a what? A constant. Okay, so if we have the gradient of phi is perpendicular to phi. Let's get that. Whenever we perform a gradient, we have a gradient of a particular function. It is, number one, it's a constant. Number two is perpendicular. Okay? These are perpendicular to each other. So when you perform this operation for gradient, you're finding the perpendicular. Okay. Now, how do we find the normal? We said we're trying to find the surface normal. So how do we find the normal? We find out what the gradient is, and then we divide it by the magnitude of the gradient. That's simple. The magnitude of the gradient. That's all we have to do. So let's look at this. This function, or this graph here, shows us that what? Z is equal to 4. Okay? This is Z, this is X, and this is Y. This is Z. Z is equal to 4, that plane. So with Z equal to 4, we have our equation, which has to be a what? Constant. Okay? So we're going to take this specific equation, okay? Z minus 4, where Z equals 4, Z minus 4. And if we take the what? The partial with respect to x, y, z. Okay? If we take the partial with respect to x is 0, with respect to y is 0, with respect to z, it's it's 1. And it goes in the what? K direction. And guess what? There we go. Perpendicular to what? The plane at z equals 4. Here's 4, and it just goes all the way across. Let's look at another example. Let's look at z equal to x squared plus y squared. Okay? This is what our curve looks like. So, we have z is equal to x squared plus y squared. What is our phi? Okay, we're going to set this equal to 0, so it's x squared plus y squared minus z equals what? 0. Then we take the what? The partial. Take the partial with respect to x. We get 2x, and it's in the odd direction. We take the partial with respect to y. We get 2y in the j direction. And if we take the partial with respect to minus z, we get a minus 1, which gives us a minus k. Okay, how do we find the normal of this function? The normal of this function is 1 over 1, right? It's the magnitude of the gradient. So the magnitude of this gradient is what? 2 times 2 is 4. 4 plus 4 is what? 8. 8 plus 1 is what? 9. So this is 3. The magnitude of this is 3. So it would be our particular function we have here our gradient divided by the magnitude by 3. I hope you're getting the points to this. And look at this. These are the directions of them perpendicular. Remember, everything is perpendicular. There's infinite number of points. And these are the 3 points that are perpendicular to our original function. Just as our original function here was z equals 4, this is our, and we can see the k direction is what? Perpendicular to that surface. The same thing here. We can see that these should be perpendicular to the surface. So here's some more practice problems for you to do. Okay, and now we're going to look talk specifically about gradients in cylindrical coordinates. Okay, when we talk about these gradients, they have different forms depending on what coordinate system you're using. Okay, if we're using the cylindrical coordinates, remember, we just was using the polar, we were just basically really using the rectangular coordinate system, okay, because we used x, y, and z. So now we know that we talked before that this changes. Okay, and so we have, instead of x, y, z, we have what? R d theta, and we have z. So as you can see here, this is our, let me see where my r is, okay. Let's see where our r d theta, this is our r. R, remember we said, it will sometimes be called rho. Here it is called rho. This is our r. So this is our dr, okay, which relates to this graphically. And then we have r d theta, or d phi. And then remember they interchange phi with theta. Okay, so it's r d theta here. That's what we have here, r d theta for this curve. And then we have what? Just z, dz. So we have our height, our width, and our length. So it's length times width times height. So this is our height, this is our width, this is our length. Okay. So now what about if we're using cylindrical? Okay. Okay, as we continue in cylindrical, notice what we had. You see here, we're still using what? Rho, phi, and z. And our cylindrical form. As you can see, this is like a cylinder. And this cylinder is the same cylinder as it was wrapped here, but it's just a piece cut out. As we have this point here, we have a z component which is perpendicular to this point. We have a what? A rho, a phi, and we have a rho, or our x component. So as you can see here, that you have this rho, okay, here, and you have your z, which is here, and you can see these two form a what? A plane, okay, which they're representing here. Then we have perpendicular to this point, we have our phi, okay, which is perpendicular to that point. So as you can see, you have 3 dimensions here, and each one of these are perpendicular. Okay, we can use that as our unit what? Our unit vector. Okay, so now let's look at its spherical coordinate system. Okay, it's different units yet again. Okay, so we added this component here graphically, d theta. Okay, down here d phi. Okay, and we added what? R times the sine of theta d phi. R times the theta d phi. Okay, and so now our gradient changes. Okay, we have our gradient as relates to what? R, theta, and phi. These would be our unit vectors. Now we took the partial as it relates to what? R. We take the partial as it relates to theta. The R comes out because it's a constant. And then we take the partial with respect to phi. And our R times the sine of theta comes out. So that was different. Over here we had Z in our cylindrical coordinate system. So as you can see here, this one is now a sphere, like a globe, where the other one was not. It was like a cylinder. So we have our phi here, our y components, our x component. Here we have our theta, and here we have our r. So you have your r, your theta, and your phi. But before we had r, theta, and z. And then before we had x, y, z, and before we had r, just r theta. Okay, so these are very important things that we need to look at. So, I'm going to give you a few more problems to work. Okay, so please work these